Before we dive into new formulations of functions, it helps to take a step back, though, and ask a more general question about what is a function in the more general sense, and what are the boundaries of what defines a function? What are the things that we can play with, and what are the things that we can't? Going back to the original definition you probably saw of functions, is that a function is a rule or process that assigns to each input a corresponding output. And there's a little subtext here that's usually implied by the context, but there's a maximum of one corresponding output. In other words, we can only get one output, not two or three or four or five, and some inputs might not have an output at all, like square root of -1 doesn't have a real output. With that idea of an input being translated into a single output, then what we can look at is how these kinds of functions might be expressed or formulated. So let's take a look at the example on the next page. Fairly simple. We're going to have a wheel of radius 1, and when we draw that out, just to be clear here, the radius is always 1, and we have a green dot G, and what we're going to be doing is turning the wheel counterclockwise by an angle of theta. So we're going to be going in this direction here, and the output, here's our input here. Our output is going to be the height. So there's a lot of things we could use as an output. We are specifically going to use the height of the point. So for example, if we were to rotate to this position here, this would define a range or an angle here of theta, and the h that we're interested in would be this vertical height drop down here, h of theta. Now, if we take a look at that construction, then there are various ways we can try to examine how theta and its output are related by this function, by this verbally described function. One thing we might try at first is simply to sketch a graph of this relationship. So we draw ourselves some axes here and label them as theta as the input and h of theta as the output. We know that we can sketch a few sample lines here, and when we know that theta is 0, the height is going to be 0 because we're not elevated above the line there. Then we can erase that and imagine a little later on, let's take pi over 4, which is 45 degrees. So then we have a theta value, and we're going to get a value back for that. Well, we know the radius is 1, so it's going to be something a little less than 1. So let's put 1 in our chart here, and at pi over 4, we're going to have something a little less than 1. Actually, that's making me think, another way to tie these two together might be a table where we have our theta and we have our h of theta, and we put in some sample values here. We're using radians because we're in a calculus class as opposed to degrees. Keep that in mind. That'll be our common thread as we go through this. 3 pi over 4. We can compute some height values for these. And if you remember your trig off the top of your head, you'll recognize that the side length here is in fact the sine of theta, the height. And so we do these calculations and we can get sine of theta when theta is 0 is 0. Sine of pi over 4 would give us 1 over root 2. When we get to pi over 2, erase these. If we go right to 90 degrees, pi over 2, then we're going to have, of course, a height of exactly 1, and that's going to be in here. And when we go even further, we're going to get back to 1 over root 2, and so on. In fact, we're actually going to go negative afterwards. With that construction, we can actually build our graph out, and we know, in fact, when we reach pi, which is the same as a half circle in our radian measure, we're going to be able to return to a height of 0 when we move our green dot all the way around. And then we are going to go and do the same thing, but in the negative heights, like so. And we simply extend our graph to match that. And we would end up back here at 2 pi, and if we wanted to, there is no restriction given, so we can imagine this repeating itself forever as we simply watch the green dot traverse around that circle. With that simple exploration, we've actually highlighted most of the ways that engineers and mathematicians use functions. If we take a look at what we have here, we had our verbal description. We built a graph, either both as a sketch or as a more detailed plot using sample points. And we actually defined, through trigonometry, a formula for that relationship. If we know the angle, we can compute the height of the point on the circle as it goes around the trajectory, and that height is defined simply by the sine of that angle in radians. And so we get this collection of tools that we can use when we're trying to describe functions. The idea is to emphasize that a formula, which is usually what we think of as a function or identified with a function in a mathematics class, is not the only way to describe functions. Very frequently, we are going to have tables of data coming from some kind of sensor information engineering, and that is going to be the definition of our function in a way that may not even be available as a formula. Graphs can also give us some insight into the structure of a table of data or a formula, help us to understand what we're looking at in a different way. And of course, the verbal descriptions are usually where we start, in fact. Those are the definition of the problem, and then we go and dive a bit deeper and get more quantitative information through the other representations. But the key thing is, don't limit yourself to thinking of functions as simply formulas. There are lots of alternatives out there. So with that idea captured, that we shouldn't limit ourselves simply to formulas, we still want to keep this general idea of a model of a function where we have an input and an output. That is going to be consistent across a variety of different ways we can develop formulas. Just a reminder about terminology, we would call the output here the dependent variable, and the input variable over here is what we consider the independent one. We don't have any control over time. Time marches on, and so it's independent of our choices. The dependent variable depends back on time. We won't use that phrasing that frequently in this class. We'll typically talk more about inputs and outputs, but the phrasing will occur from time to time. It's just important to have that in mind, especially when you do experimental courses like Mod 2, then you'll definitely be using this kind of dependent and independent terminology. Now let's go back to our canon of knowledge that we already have, and we're going to take a look at functions that you're familiar with, and note specifically that by and large, these functions would have single numbers for inputs and outputs. For example, let's do y equals x squared. We would have a single x value, and that would give us, as an input rather, and that's going to give us a single y output for each x. There's just one dimension of input and one dimension of output. And of course that same thing applies if we'd written it as f of x equals x squared in function notation, same idea. Think of the other functions we've seen, exponentials like e to the t, x equals e to the t, again, one input, one output, y equals cos of x, or cos of 10x, let's change it up, and other functions, logarithms, g of x equals ln of x. In each of these cases, we have one single value. We put a single number in for x, we get a single number y back, and we can then graph that by plugging in a range of x values to get a range of y values back, and that would give us both tables and graphs if we wanted them. In the upcoming videos, we're going to see how we might expand this idea of a function so that we have more than one input, maybe have an x and a y come in and give us a z back. Or alternatively, what if we had time coming in and we get not just an x value back, but maybe a separate y value? What would those kinds of formulas look like, and how would that play into the calculus rules that we've already used? That'll be what we're exploring for the rest of this topic.